Hey guys, so today we're going to learn about Thevenin's and Norton circuit. So let's get into it. Let's say you have a circuit, a complex circuit, let's say, that has multiple current sources, resistors in series, in parallel, and multiple components offering impedance. And then you have your load resistance or your load connected across these two terminals right here. So when it comes to these kind of circuits, if you want to know that, okay, as an engineer, I'm going to connect a load to this circuit, and I want to know what's the voltage that I get, or what's the current that's going to flow through my load, or what's the voltage going to be across my load, you need to do some really complex math if you want to know, if you want to solve for that, and especially going in this direction towards the left. So this part of the circuit right here becomes if you have this part of circuit and you just want to measure what is current and what is the voltage across your load right across these two terminals, it becomes very complicated. That's where your Thevenin's and Norton circuit come into play. So this is a complicated circuit. So according to Thevenin circuit, this entire portion, what I've shown you in the red, can be converted to just one voltage source and one resistance in series, and then you can hook up your load to it. And this is going to be your load. This resistance is known as Thevenin's resistance, and this voltage is known as VTH. So basically what it's saying is you can do some kind of analysis where you take all the complex circuitry right here and you can convert it to one voltage source in series with one resistance. This is the Thevenin's circuit. All right. So similarly, if you want to get a Norton circuit, it's a similar way of simplifying it. The only difference is in a Norton circuit, you would have a current source in parallel with an equivalent resistance, and then you would hook up your load right here. And this resistance, of course, will be known as the Norton's resistance, and this current will be known as the Norton's current. So I hope you got what I'm trying to say so far, that whatever I've shown in the red box is equivalent. So you can take a complicated circuit, disconnect the load, and you can either simplify it to get a Thevenin circuit. So this, I'm going to show you right here. So this circuit right here can either become a Thevenin circuit or it can become a Norton circuit. This kind of analysis makes it very, very useful. Let's say you're an engineer and you want to know what's the current flowing across the load. So to measure the current flowing across the load, you would need to measure what's the current that you're getting here. For that, you would need to apply a lot of circuit theorems laws, like Kirchhoff's laws, and it is going to take forever. But if you use Thevenin's theorem, you can simplify that and speed up the process. It makes it a whole lot easier. And also, especially if you have in power generation, if you're working in power generation, you got multiple generators and you want to hook them up together. And they provide different voltages. So let's say this provides V1, this provides V2, this provides V3, and you don't know what's the equivalent power that you're supplying to the grid. So one way to do this is you can convert this to a Thevenin's voltage and this to so you can get the equivalent Thevenin's circuits, or better yet, you can get Norton circuits here. If you get the equivalent Norton circuits, Now, if these are connected together, it would just mean that all of these three, generator 1, generator 2, generator 3, are just connected in parallel. So that would mean you can just add up the currents. You can add up the currents. So if you add up the currents, this would be your total current, and you would get an equivalent resistance, which is these three resistors in parallel. So then you would have the generator equivalent being something like this. You would have one current source with one resistance in parallel. Forgive me for the messy diagram. Alright. So then you can go ahead and keep the current source the way it is, or convert it to a voltage source in series with the resistance. Now you can say, hey, if I hook up my three generators, which have different capacities, I'm gonna get this voltage, which is the Thevenin's voltage, and the impedance offered is gonna be this impedance, which is the Thevenin's resistance. Alright. So these theorems are very useful when it comes to the real world of power systems engineering. Another thing you want to know is if you have a Thevenin circuit which looks like this, you have a voltage source in series with a resistance. And like I said, this is the Thevenin's resistance, this is the Thevenin's voltage, and this is the Norton circuit. I'm going to draw here. Norton circuit right here. So these two circuits are interchangeable. So if you have a Thevenin circuit and you want to go to a Norton circuit, you can use simple Ohm's law to get your Norton's current as your Thevenin's voltage divided by your Thevenin's equivalent resistance. And if you want to go the other way, if you want to get a Thevenin circuit from a Norton circuit, then you would just do it would be the Norton's current times Norton's resistance. So now you see how simple it is. So if you have a complex circuit, you can either change it to a Thevenin's circuit or a Norton circuit, and these two circuits are interchangeable. And this voltage, VTH, the Thevenin's voltage, is the voltage measured by disconnecting the load and is known as open circuit voltage. So ideally you would have your load connected right here. What you would do to measure your Thevenin's voltage, to get your Thevenin's voltage, is just disconnect the load and put a voltmeter right here and measure the voltage. So that is how you get your Thevenin's voltage. And to get your Norton's current, IN, the way you would find it is, so ideally you would have your load connected right here, and in order to find your Norton's current, you would disconnect the load and then you would short this and you would find the current flowing through this, and this is known as short circuit current. So you disconnect the load and then you short it, and then you find what is the current that flows if the load is absent, if the load is zero. So that then you would get short circuit current. That is how you find Thevenin's voltage and your Norton's current. Okay. And the only thing left to do now is finding the Norton's or Thevenin's resistance. And remember, these two are equal. And to better understand this, let us go ahead and solve a problem, so that way we can better understand how to find these circuits. All right, thank you guys for watching.